All right, good morning, everyone. Good morning. I see some more people coming in. Please take a seat. Thank you all for coming in this crisp Seattle typical winter day. So it's really, really a pleasure to welcome you to the second TVM and Deep Learning Compilation Conference. My name is Luis Sazzi. I'm going to be your MC in the keynote. And we're going to have a fun keynote. It's not going to be just one person talking for an hour. We're going to do like super high frequency context switches here. And first I wanted to say that we're super pleased in how the TVM related events are going. You know, this is actually our third event at UW. It's the second conference. The first one was a small workshop. We also had a couple of meetups in the Bay Area in Shanghai this year that were also pretty well attended. And this year, we had 200 people attending, which is pretty great. It was great to see. And seeing the growth, I'm so glad. If you look to the right there, there's a stadium. You know, that's where, you know, we're putting a reservation for the stadium for our next meetup next year. Okay, so, but I wanted to reflect just a bit on why we are here, right? So in the machine learning era, as opposed to the software era, we just write code and run. You know, the way we solve problems today, we collect data and model templates. We train these models in the fastest possible machine you can find, the most expensive typically, and then you want to run it you want to run inference on a fast enough and cheap machine. But if you look at the trends in terms of inference, so there's interesting data that Eugenio Colucciello from Purdue and Micron has been collecting on the trends of model sizes in terms of parameters and also computational cost. It's growing super fast, both model size and computational costs. It's kind of amazing, mind-boggling to see models not just with hundreds of millions of parameters, but also approaching 50 to 100 billion ops for one single inference. So that's inference. But if you look at training, OpenAI showed this plot, and a lot of people have been showing so far, but I want to add a twist to it. So what this plot shows is the computational cost of training state-of-the-art machine learning models. What's interesting here is that the trend is roughly computational cost in number of ops is growing roughly 10x per year. Okay? And now let's look at the one on the top right there, the AlphaGo 0. So if you were to train that on EC2 today, it would cost about $1.5 million. Now, to put that in perspective, let's see what you can buy with $1.5 million. So here's one home in the Bay Area. So now you can choose. You either, train that model or you buy this house. I'll let you make a choice. We can do a show of hands here. Who would train the model? All right. Okay, who would buy the house? Oh, interesting. More people would train the model. Interesting. All right, cool. That we had the right crowd here. But I'm sure you've been following all of the comments people have been making about the carbon footprint of AI. I think AI is probably getting too much of a bad rap on this. It's not just AI. A lot of interesting computational problems have significant carbon footprints. But AI specifically, given it's so popular, is getting quite a bit of attention because of its energy cost. But with all this aside, it gets even more serious. This is for the computer architects in the room here. You've seen this plot many times, and what this is showing is that even though we're still getting more and more transistors on a chip, we're having single-thread performance tapering for a while. Even number of cores is starting to taper, and maximum frequency, typical power that you can afford to pump into a single part. And at the same time, if you were to plot the computational cost of machine learning, it's growing much faster than anything else you see here, right? So there's a big oops that we need to somehow bridge the gap of these two exponentials. So I think it's fair to say that the impact of machine learning will be limited if we don't squeeze as much efficiency as we can. Okay? And it's really that really means optimizing models, optimizing software and hardware is really, really key. And with that in mind, there's this perfect storm brewing right now, right? So we have a permanent explosion of useful models that we care about, a bunch of requirements on top of them. These models, to be useful, they have to have the right cost, the right latency, power requirements, security and privacy now is getting more and more important. And we have a second Cambrian explosion of hardware targets, right? So this is because of Dennard scaling limitations and just say Moore's law approaching its limits. There's a lot of incentives to do hardware specialization. All of the major IT companies are building specialized hardware for machine learning. And there are quite a few startups, like almost one every other week, building new chips for machine learning. And then in the middle of this all, bridging these models and these hardware backends, there's this growing, fast-growing, but also quickly fragmenting software ecosystem on top of this. That leads to a really interesting scenario where we have this growing set of, this is what we're showing here, is that Terry Moreau put this really nice plot here showing some of the major deep learning focused software stack packages that appeared. And it's kind of amazing that Halide, who was really transformational in thinking about how we decoupled schedule from programs, started only 6 years ago. And then, in 2017, we had over a dozen major packages released. And now it's kind of slowing down a bit. Hopefully that's because there's some consolidation going on and people are learning a lot from this diversity and focusing on what actually brings most impact, okay? But a lot of these require a lot of hand tuning. So despite all of this effort in bridging the gap between models and hardware, you still have to do significant amounts of hand tuning. So having full automation would be really, really nice. And that's really what we set off to do with TVM. So TVM has been around for, say, almost 3 years now, and it's going strong. And here's one picture of what we see as a current dominant deep learning system landscape, all the way from orchestrators on the top that orchestrate execution of inference and training in the cloud, and then frameworks, deep learning compilers that all of the major, a lot of the major hardware and system providers are building their own compilers, and then specifically the kernel libraries built by hardware manufacturers that are often hand-tuned, and then a bunch of hardware at the bottom. What we set off to do with TVM is to see if we can actually bridge from framework down to hardware directly with as much automation as possible. So we definitely want to contrast the fact that a lot of the effort today in getting models to run efficiently on hardware has been largely focused on a platform-specific way. If we can automate the process of going from framework to how things run, in the actual hardware, we can actually increase reach, decrease platform dependence, more performance portability, and so on. And a key to doing that, the way we see it, is really, I think, this drawing hands from Asher shows how we think about this, right? Is that we see, using machine learning for better machine learning systems as key to do this, because the design complexity got to a point where, we can't do with significant automation and significant really, really, really good tools to reason about large parameter spaces and so on. So that includes things like how do you do model optimization strategies and find the right parameters, efficient operating implementations like what AutoTVM does. You're going to hear more about this today. Data communication patterns, model hardware code tuning, searching for efficient, even hardware designs. I think it's fair to say that we're getting close to being able to going from a model straight down to hardware design that serves that model really, really well. Okay? So now let's just reflect a bit on what happened this past year in the community, and then we're going to do a context switch here. So in this past year, we increased model coverage quite a bit. Now, with the close PyTorch integration and the Relay VM, which you're going to hear more about today, we're able to now run models like BERT and single-shot detection. So this is at the very top. We increased model coverage quite a bit. But also more hardware backends. We have major hardware backends used in production now, Cortex-M and RISC-V, and even some DSP cores we're going to hear more about today. And then in between, we also added more optimizations in the stack, things like automated quantization and more data layout optimizations as well. But I would say one of the things that is most exciting is the fact that we're putting quite a bit of effort now as a community in usability. This is more tutorials. We ran a tutorial at FCRC this year that was really well attended. And we put quite a bit of effort in having tutorials that are easy to run and follow, and we recorded videos people have been using and so on. But community development in general has been going super well. So Tianqi is going to talk more about this later in the keynote session here, but from last year, there was 70% growth in the number of contributors to the project, and today it was just under 300 people actually writing code, which is really great, both from academia and industry. And then this being hardened by industrial users. We are very, very thankful by industrial partners that contribute the code and also try it out and see what works and what doesn't and help us harden this. Okay? We also incubate as an Apache project. We find it super important, especially for more widespread adoption. So incubating as Apache gives independent governance. It's not just a bunch of people sitting in a room somewhere here. It's actually people that are invested in its success and use it and depend on it, have a say in where the project goes. But also, most importantly, it allows competitors to collaborate And I think this is super important, especially when talking about open source compilation optimization stacks. Okay? So with that, I would say like a big thank you to the community. We really, really, like nothing that happened would be possible without everyone's contribution. So this is really, really, really key. So thank you. With that, now starting from the hardware, we're going to pass the token to Jeff Gelhar, who is at Qualcomm and just fresh off of the plane from Hawaii, where they had some fun announcements, right?
Yeah.
So.
Thank you. Thank you, Luis. Thank you always. Again, I'll echo, I was here last year, and it just feels like there's so many more people and so much more excitement about what we're doing. Okay, real quickly, who am I? VP Technology at Qualcomm. I run Qualcomm's AI software project. I recognize a lot of faces in the room. And what I wanted to do is just give you a broad overview of kind of what we do, how we think about AI at Qualcomm, and then also a little bit about the problem, as Luis just highlighted, how do you deal with hand tuning all these different architectures. So maybe I'll do this first to put it into context. You can see the recorded videos. We announced the two new flagship parts yesterday in Hawaii, actually starting on Tuesday. The Snapdragon 5G 765, fully integrated. You can see these parts later. I have them with me. And our flagship part, the 865, also a 5G device. You can read about the rest of it online. But when we think about what are we going to do with these parts, and in particular with AI in general, and then specifically TVM? We announced a cloud part to Luis's comment about what OpenAI said about performance, scaling, and power. We're not the only ones. We understand that. But we have a history in high performance, low power compute, and so we think we can bring something to it. And then 5G to connect it, and then edge AI, right? So we're thinking about the world in a way where everything's connected and everything's running AI, and making everybody's lives better, right? And the way we do that is we do have a Qualcomm AI research team. We have, of course, a product team that builds chips and does AI. And builds networks. So we're a life cycle company. I think the one thing that makes Qualcomm maybe different than some other companies is, I'll say I've been there a long time, we never invent just a piece of paper. We always build a prototype of it. So when our customers come and say, well, how's this going to work on this piece of hardware, this piece of software, we've generally tried it at some point, even if it's not a commercial offering from us. And so you see that the problem might start as a research problem, like in some sense TVM did, or it might start as a platform problem, like a customer has a problem, or it might start with, hey, we're trying to solve a problem with AI, right? And you can see more of that if you follow up on YouTube, the talks from the Qualcomm Snapdragon Summit. In terms of products, to kind of orient it, Luis already talked about sort of the diversity of software products, and I think we're a little bit to blame. So you'll see us working to try to fix that. But the thing we started out with was the neural processing SDK. It's still the most popular way to get onto Snapdragon. And frankly, there's over 1 billion AI-enabled devices. 1 billion AI-enabled devices powered by Snapdragon. The second thing is Android and an API from Google. Google's partner. And then I'll talk about this in a second, and you'll hear more about it in the technical talk, Qualcomm Hexagon neural networks. And of course, that diagram on the right really illustrates the fragmentation that you get when you have unbounded innovation like we have right now. Okay, so let's zoom in on that diagram real quick, and then I will leave the rest of the time for the next speaker. So here's kind of the stack. It's obviously simplified a little bit, diverse hardware. And the question is, okay, so what about this piece right here? This is where we hand tune today, hand build for the most part, all of these libraries, all of these operators, as you know, for neural networks. And specifically, you'll hear a little bit more about this later, Hexagon and N library. So this is the kind of key math library, if you will, that runs on top of Hexagon, and it's highly tuned for our DSP architecture. And it currently supports about 100 hand-tuned, highly crafted operators, and very successful. Lots of handset manufacturers have launched all kinds of devices with that stack. But what's the problem? It's handwritten, it's optimized. There are 3 variations of the instruction set. It goes into gazillions of these kinds of chips, each with their own little variation of TCM size and clock size and bus arrangement, right? There's a lot of variables, right? And we've written these extensions for the vector processor and the tensor accelerator. So both for 2 and 3D tensors, you have to write, and it turns out that they have slightly different instruction sets, and so you have all this inherent complexity. Incredible demand. Our customers, the number one thing is, can I have a new operator? Like I would say, the vast majority of our feature requests run like, can I have a new operator? And when can I have it? Like tomorrow. So obviously that's a problem. And so the idea is, Hexagon is super power efficient, it's super flexible, but I'll leave it to the Hexagon guys in the room who are here from Austin. It's not the easiest little machine to program. And so, getting the most out of it really takes kind of specialty craft. And that's why, we're interested in TVM. So we see TVM as key to access on Hexagon. And I got a question, over breakfast. Are you going to use it for everything? How does it fit in? I'll make just a little shout out to what we announced in Hawaii. We are announcing user-defined operators. So this is the ability to plug into our frameworks operators that are written, by our customers, by our partners. You'll be able to do it with OpenCL on the GPU, but notably you'll also be able to do it on Hexagon. And so TVM is part of that story, where you'll be able to use TVM to write operators, and there'll be more details later in the day. Okay, key innovations, just to kind of recap, so you kind of key takeaways. We're leader in AI power silicon, right? Right here, I got the leading chipsets in the world. Respectfully, for those of you in the room who are also semiconductor manufacturers. Hardware, Hexagon hardware is high power performance, but, to be plain, it's not the easiest machine to program. And that's why we're here. We've really had great success with things like Halide before TVM, so domain-specific languages for, say, computer vision like Halide have been big standouts for us, and notably big manufacturers that you would be familiar with have used Halide with Hexagon to do their CV processing, so we look forward to the same sort of experience with TVM. And I didn't talk a lot about Qualcomm AI Research. You'll hear a little bit more of a shout out later, but a lot of the innovation we're doing with Qualcomm AI Research is focused on things like quantization, but also on things like hardware-specific kernel optimizations, domain search, and that kind of thing. And I'm super excited to hear what everybody else in the community is doing in the same space. If you think there's a chance for further collaboration, I can definitely connect you to the research guys. So with that, I will leave it to the next speaker.
Cool. Thank you. So now that we heard from Qualcomm, we're going to hear from Ida Wang from AWS, so, who also just announced new hardware in the last few days, right? So, Ida, thank you. Thanks for coming.
All right. Thank you, Luis. Thank you, Jeff. So I think the presentation are really nice and slides look very good, which makes me kind of nervous because in the next 3 slides, we are going to see pure text. So bear with me. My name is Ida Wang. I'm from Amazon. I would like to share with you about the story in Amazon, like about how the TVM meets AWS. So before that, I would like to give you a little bit setup about AWS AI, so what we are doing. So basically, at AWS, we are providing the broadest and most complete set of machine learning capabilities to different kind of customers. So no matter which domain you are from. So for example, if you are just an AI user, you are welcome to use our AI services on the top. So you don't need to know much about the technology. You just need to use it to recognize a face, to recognize a text, or to translate text to speech, so on and so forth. And if you are a data scientist, you are welcome to use our software suite called Amazon SageMaker, which can help you train a model, tune a model, and also do auto-tuning and do fast inference, things like this. And last, if you are a machine learning practitioner, you would like to build blocks by yourself, we provide you all the mainstream frameworks and infrastructures that you can play with by yourself in whatever way you want. So as a result, we are proud to say that more machine learning happens on AWS than anywhere else. And more specifically, you can see that 81% of the deep learning in the cloud happen on AWS. So you can see that, this is very critical. It is very critical to us to have good performance on deep learning and have a high performance deep learning compiler will be very important to us. So now I would like to talk to you about how TVM plays a role in AWS. So because we are also here last year, so I would just like to focus on mostly what's happening in the past year. Okay. So first, TVM at AWS is we do it as a cloud service. Last year, our engineering manager, Vin Sharma, talked to you about Amazon SageMaker Neo here. So our slogan is train model once and you can run everywhere with like up to 2x speed up. So the service is online for a year. Now we have like quite some users running their models, optimizing and compiling their models for different kind of hardware. So next is a solution. So for SageMaker Neo, you can treat it as more like a generic solution. You give us a model, give us a platform. We try to, on the cloud, automatically optimize and compile it for you. Then if the solution here means like more like a specific solution. So like if you have a very specific request, you can talk to us. We may be able to do something for you. Like we can run a number of models on a number of AWS Amazon EC2 instance in the fastest performance. And also, we do not limit ourselves on the cloud. We also do things at the edge. So one example is like we optimize the Alexa wake word model on all the Amazon Echo smart speakers. So now, if you don't know now, now you will say that like at home when you say Alexa, if you give you a response, actually it's powered by TVM. Okay. The third thing is like we also do not limit ourselves inside Amazon, so we also actively talk to a number of external device makers, including Qualcomm, so to see if we can collaborate with people outside to do better things with those chip vendor makers. And also, we do it as a research project. That's just like papers. You know, we are scientists. Some of us are PhDs. So PhDs are trained for writing papers. So you do not write papers, you feel the life is not complete, right? Well, but this is, kidding, this is not the main reason. So the main reason here is like, you know, deep learning compiler is more like uncharted territory. So a lot of things that we would like to do, there's no existing solution. So in order to keep pushing forward, we would have to, and we are pleased to do some research to work on the things that we are interested in, and we would like to share our results with the broader public. So so then we write papers. And last, TVM is a compiler. We treat it as a compiler. So Luis just mentioned, like we launched AWS Inferentia powered EC2 instance just a couple days ago. So for Inferentia, we are using TVM to, we are building our compiler on top of TVM. Okay, so this is TVM at AWS. How about the other way around? What are AWS doing in a TVM community? So first, we are also we are very proud to be one of the major contributors as a group. In a community, we joined the effort from the very beginning, so almost 3 years. And in the past year, we have leading and collaborating in a few major features here. I just give you some name here. It might be incomplete, and I'm not going to dive into the details. But the point is that we are working, okay? And the last thing is like, besides the technology part, we are also doing service in the community. We have 2 PMC members, 8 committers, and 14 reviewers. And I strongly believe that the number is growing. Also, we do activity participation and leadership in the community. We host meetup, and we lead the some version release. We actively talk to people. We actively participate in the Discuss forum, and so we are very happy to see the community growing, and I'm also very happy to see so many people today here in the room. So that's it from my side. Thank you.
All right. Thank you. So now that we heard from hardware and from both companies building hardware and building systems, we're going to hear about a new company, Jason Knight.
Thanks, Luis. Yeah, I'm here from OctoML, but before talking about that, so I want to start with a prediction. And as any good prediction should be, it's a bold one. So if N is the number of people building machine learning models, and by building I mean training, deploying, et cetera, kind of anything around machine learning models, and M is the number of software developers, then today N is much smaller than M. But I argue that it will be and should be the case that N will be much larger than M as we go into the future here. And why is that? One reason is that if you boil it down to the fundamentals, building software requires learning a rigid set of semantics to describe computations for a computer, whereas machine learning is a much more natural and flexible way of teaching a system to do some task by showing it examples or giving a reward signal. And so why is this not the case today? That it seems simple. Like I give examples to my kids or my dog, and it learns. And why everyone can do that, but why are so few people training machine learning models? And the reason is that deep learning deployment should be easy, but it's not. It's not today. It requires a large amount of complexity and expertise. And we want everyone to be able to handle and deploy and build these deep learning models. And so, why is it complex? Why is there pain here? It's across the stack. Model ingestion, conversion from one framework to another, software fragmentation, performance estimation and comparison. How do I, what is it going to perform on this device versus this device? I have to set up new tool stacks, et cetera. There's a Cartesian product of models, frameworks, and hardware, and the support across those. If you're doing code gen, there's a whole raft of options that I have to learn and figure out kind of what I want to do, et cetera, et cetera, et cetera, right? And so, coming back to this vision of deep learning deployment should be easy for everyone. TVM is core to making that happen. It's the core foundation of techniques and compiler automation that allows the building blocks of building this future, but it's only the first step to doing so. And so, what are we doing about it? This problem of where the complexity threshold is too high today for more people to be benefiting from deep learning and machine learning. The first thing is we're strengthening the core. So reinvesting and continuing to invest in the TVM open source project and ecosystem. And I'm going to talk more about that in the next slide. But this is the robustness and resiliency of the project, accessibility to new developers, the community and model coverage, et cetera. And we're OctoML is a company which I'm going to get to, invests in TVM, and so you'll see several talks today by OctoML members. Tianchi will be talking about unified IR and many other things. Jared will be talking about dynamic execution, Logan, micro TVM, and then I'll be talking about OctoML as an investment in the ecosystem later today. And then also Josh in the back has been working on transformer improvements in the TVM ecosystem, and Zhiheng on automatic quantization, which we're not talking about today. And but coming back to what we're doing about this, so in addition to investing in the core, we decided that we needed to form a company to continue building upon the foundation of TVM. And so I'm going to be talking about that more in terms of what the first steps are later. But so OctoML is a company designed to make simple, secure, efficient deployment of machine learning models more accessible for anyone everywhere. And we do that by driving TVM ecosystem and community and adoption, and by expanding the set of users who can deploy machine learning models by layering these services, automations, and integrations on top. And so OctoML and the Apache TVM ecosystem, kind of as Jeff and Nita mentioned earlier, it's a synergistic relationship between the two. And so this is us as of today, the Octonauts, we like to call ourselves. Which, yes, it is a children's show if you have kids, which is even cooler. And yeah, so we're all around, so feel free to grab one of us and talk and chat. But come to the presentation later today, I think 2:30ish, to learn about our first product, the Octomizer. And a little teaser, it's a software as a service product offering around TVM. Running across cloud, on-prem, et cetera. and you'll see more later. And feel free to reach out and follow us on the various channels and reach out directly as well. So thanks.
Thank you. Octa now, it's here. All right, so now one more context switch. You heard me mentioning broadening model coverage earlier today, and this is a lot to do with the work that's going on the Relay IR that Zach Tatlock, hi Zach, who not only being a great member of the community, our evangelist, is also a human megaphone, right? Do you need a microphone? You probably don't need.
We need a microphone.
No, so that's right. All right.
Okay.
All right.
Thanks. So, I just wanted to quickly talk about some of the things going on in Relay over the past year. We can sort of, to get context, hop in the Wayback Machine and teleport back. And for those of you who were here last year, you saw Jared Rush, my student there in the back, giving a talk about the motivation, the need for Relay. Now, you can't really see in the slide. It's a little bit blurry. So just to recap, what's going on is that increasingly state-of-the-art models depend on more and more programming features, right? They want data structures like lists, trees, and graphs. They want control flow, branches, recursion, and they want all of that to work together, right? So they want whole program optimizations and analyses that allow each of these things to contribute to one another.
Just because we're being
we're recorded.
and recorded, yeah.
Oh, okay. I guess I'm not loud enough to reach the entire internet. But yeah. And we see this, right, in the way that frameworks continue to evolve and change. So these features get added, but sort of one at a time, and they often don't work smoothly with each other. So we have this challenge. We want to basically have expressiveness, have everything work together, and have performance. And the tension is that you usually can't have both, right? Normally, when you get expressiveness, you lose some level of performance. So, we decided to take a crack at it anyway, despite the fact that we're a small team of PhDs in a university setting, and thought, when I think performance, I think Haskell. So why don't we start with functional programming? Now, I don't know if maybe there's not a lot of Haskell hackers here. But there's a lot to be said for taking this approach. So one thing is that you get a nice clean semantics, which does ease analysis and optimization. You also get all of these programming features that people want to use to express state-of-the-art models, right? We have recursion, we have control flow, we have data types. And it's easy to do mathematical analysis for things like adding automatic differentiation. So we built this, but of course it wasn't immediately clear that we're going to get the other side of the goal. Are we going to be able to retain performance? And so I'm really happy to report that after a year of really intense engineering, the answer is yes. We haven't lost anything. This is low cost for adding these programming features. Across a range of traditional vision learning models, we match NVM's performance. So that's great, sort of achievement unlocked, right? We wanted to have both these things, have these high-level programming features, and retain the performance, and we did that. But there's a couple of questions that you might be sitting with still. One is, how does that work? How do we have those high-level programming features and still maintain the excellent performance of an NVM? And the second is kind of, so what, right? We're just matching what an NVM could already do. So really quickly, I want to give you some intuition about answers to both those questions, but please do feel free to come find me or any of the Relay students. Steven's back here as well. Jared's wandering around, and I think Logan and others are around who will be very excited to talk about the project. So first, how do we get that performance? So we have a few major tricks. One is that we have a really fancy type system that allows us to write inference code that takes advantage of shape and informs the optimizer about available memory layout transformations. And so this fancy type system actually helps basically perform an analysis that lets us do many, many key optimizations. The second thing is that we have a really good partial evaluation, a whole program partial evaluator, which is able to compile away most of the abstraction that isn't necessary for any given model. So you can write your program in a high level, but the partial evaluator is going to be able to remove the overhead of fancier programming features that you don't need for this particular execution. But maybe the key thing, one of the things we're most excited about and that you can be a part of, is that Relay offers a very extensible, composable optimization pass framework. So it's easy to add new optimization passes, and they compose really nicely. In fact, there are Python bindings, so for many optimizations, you can write them in one screenful of Python. And what's neat is that these optimizations work together. So as you can see, no one optimization is responsible for performance gains across all models, right? For some models, one optimization is key, and in other models, it doesn't matter. But because we have this unified approach, these all work together in a single framework. Okay, so this is how we keep the performance. But so what? What's new? Well, what's exciting is that because it's easy to add these transformations and because we have such an expressive language, it's easy to support new kinds of models. So now we have support for RNNs and LSTMs in TVM that are really difficult or impossible to encode directly in NVM, but are natural in Relay because we have recursion, because we have loops, because we have all these features. And it's not just adding new kinds of models. Those same transformations also make it easier to add support for new kinds of backends. Right? I can do the sort of high-level transformations necessary to massage my model into a form that fits a particular target or accelerator. And so we get a lot of benefit from having these extensible, easy-to-add optimizations. Okay, so oh, sorry. And one thing I actually want to highlight, G actually issued a PR recently. Yeah. And it's not just actually the optimizations. It's also easy to plug in new code gen, right, to target new accelerators like those coming out from Qualcomm and other of our partners. So what's the takeaway? Well, the high-level thing I really want to emphasize today is that what I've been talking about so far is sort of research progress on Relay. But Relay is not just a research prototype. Relay is really become production ready. And you know it's true because Tianqi said here in the upcoming release notes, Relay's been merged into mainline. It's publicly available. It's extensible. We hope it's really easy for you to add stuff, add your own passes, target your own accelerators, add new backends, add new optimizations. We've put a lot of effort into the tutorials and documentation to make that possible. So the big takeaway, the action item, is to not be a stranger. The Relay community, just like the broader TVM community, is super vibrant and welcoming and helpful. And we would really love to have more people involved writing Relay passes, optimizations, and analyses. So hopefully next year, maybe one of you will be up here talking about the amazing things you did in Relay over the past year. And we're really looking forward to that. Thank you.
Okay, thank you. That was awesome. All right, and now we're going to end the keynote session with the one and only Tianqi Chen. Hi, Tianqi. It's your turn. So, and I would say that a lot of us are here probably because you started a lot of these projects, so thank you.
Thanks, Luis.
All right.
Yeah, so I'm going to briefly talk about what we have done in the past and what we'll be up to in the next year. But of course, all these things wouldn't happen without the help from all of our community members. And to recap, in the current deep learning framework, TVM mainly tries to automate the hand-optimized version of the libraries. And why do we need such automation? So if you look at traditional deep learning frameworks, all those data flow graphs need to offload those color nodes onto low-level libraries. Like in the case of NVIDIA, you do CUDN. But the problem is that for each of the color node, you have to assign engineers to go and optimize it. And there are definitely more than 3 engineers. As a matter of fact, that will be a huge team who go and optimize all each kind of operators that people care about. Now that if you try new operators or if you want to do new system optimizations like fuse the node together into this new blue node, it will give you better performance. But then people have to write this new blue node for that operator. That means more engineering resources. And if you try to count all the possible combinatorial combinations of operator fusion you can compose, it simply does not scale. So, and if you want to multiply that by the amount of engineering resources you want to apply, it's a very engineering-intensive process. That is why we want to use a new approach, a machine learning-based approach that tries to replace many of the human effort that bridges the high-level computational model by a machine learning-based program optimizer that automatically generates code to optimize low-level hardware. So why do we need automation? There are several arguments, and today I think it's still not very clear in a sense that there are still a huge bunch of teams going hand-optimized code, and for many big companies that is the way to go. But on the other hand, after several years on trying to bring automation to machine learning, we start to see the trend. The trend is that if you talk about traditional models like ResNet or those models that the engineers OKR are just go and optimize those models. Usually those hand-written libraries are very well optimized, and by using automation we can compete but maybe not win by a very large margin. However, if you go and talk to our customers, usually they will say that I want to run a model on my car and that model looks different from ResNet. And on those emerging models, because the engineers are not spending their effort focusing on those targets, machine learning can usually bring you a huge win, and you will hear more of the talks later today talking about their successful stories about running TVM on their model. You can try to do a exercise to think about, for every model that people talk about, think about, is that an emergent model, or is that a model that MLPerf or like a standard ML benchmark that include? And usually you will see there are a lot of interesting emergent models. Secondly, even on standard benchmark models, we can still be very competitive. The reason is that it's not like we are trying to compete with humans on the same problem, because for humans, usually when we optimize deep learning models, we will pick a specific settings like a specific data layout, specific operators. However, by using machine learning, it opens up more space for optimization by trying different fusing patterns, different data layout, and that gives us another different angle for doing improvement. And finally, by using automation to give us more automation and help us to port the same machine learning framework across all the hardware backends, as many of you will hear about today. So to recap, the TVM stack contains two-layer optimization, the high-level optimization. That's a relay IR that Zach just talked about that help us to do graph-level fusion, layout optimization, and tensor expression-level IR that help us to do low-level decisions like how do we do operator fusion and make use of the shared memory in GPUs. I'm going to switch gear to talk about a few highlights from last year that I see as a common theme in the community. This is by no means a comprehensive list. There are so many things going on, so I'm just trying to pick some of them. So the first trend that we see is that there's a trend on trying to getting more dynamism. So specifically, when we talk about deep learning a few years ago, we think about static computational graphs that tries to, you can construct your computation in a graph, and then you go and let your model run this static graph. However, increasingly, we start to see programs that have more constructions. Specifically, when you are trying to do NLP or other tasks, you might need to introduce constructions like loops or conditional control flows. In terms of data set, traditionally in computer vision, we always talk about a single tensor input with a known shape that makes it easy for analysis. However, as we start to move machine learning to more target, we start to see more kind of data structures emerging, like the parsing trees, the sequences, and other data structure. That means that we need to extend our runtime compiler framework to be able to support all these new constructions, both in terms of the program structure that we have, as well as the data structure that we support that might go beyond tensors. Jerry is going to talk more about today, but I'm going to try to give you a sense of overview. One of the most exciting projects in the community this year is called Relay Virtual Machine that tries to extend the runtime environment to be able to tackle the programs that contains the control flows and other things. Relay Virtual Machine is a stack-based virtual machine that allows us to execute many of the properties that we have. And another interesting thing is that we have runtime data structures like ADT and tuples that allows us to easily add new data structure support without having to change the system and compiler. The second trend we are going to see is that as we are trying to build machine learning onto many of the devices, besides putting machine learning onto the server devices, we are also starting to see a trend on trying to put machine learning into tiny devices. This can mean my mobile phones, but it can also mean something like your thermometer or something that runs on your camera or other cases. And one of the challenges of getting the machine learning onto those tiny devices is that many of those devices don't necessarily have a robust software support, not even operating system support. MicroTVM, which Logan will talk more about today later, is a project that tries to bridge that gap. And by providing a bare metal support of TVM runtime that allows you to run on any of the devices that support a JTAG interface, which literally means most of the devices out there. And the third highlight of community improvement in the last year is a better core infrastructure. So in TVM, we have been working on the project for around 3 years now, and while these core infrastructure don't necessarily interact with your compilation command, they are crucial actually in bringing better performance. This includes things like building better integer analysis simplification so that we don't have to spend a lot of time calculating the index when doing tensor computation, which actually consumes a huge amount of time. And another a very recent introduction is a unified runtime object protocol. So traditionally in TVM, we have objects like AST nodes, ND arrays, tensor closure, and modules. Each of them have their own runtime data structure, and we are going to unify them into a single runtime object. The advantage of this new protocol is it allows us to expose those runtime objects to many of the languages directly and allow us to directly access those objects from Relay VM runtime so that in the future we can support more richer data types in our machine learning workloads. Last but not least, one of the major design goals of TVM is always trying to be able to support new specialized accelerators. And when we're talking about new special accelerators, one of the major challenges we're facing is how do we support the increasing complex tensor computation instruction set that those accelerators provide. Traditionally, when you write programs, you only have to write scalar version program. You write for loops, describe how do you compute each element. That's very flexible and easy. When you start to try to write vectorized programs, such as those in Neo, in ARM or AVX512, you have to structure a program a bit in order to make use of those vector union. Modern TPUs or other accelerators have high-dimensional tensor instruction that can be matrix vector, matrix, or like a high-dimensional memory load with certain padding or selection properties. And it's very challenging to build systems to support all those emerging tensor instructions. That's why we want to introduce tensorization as a core primitive in TVM. The idea is that not only we want to ask users to describe computer specifications, we also want to use the same IR to describe the hardware behavior of the hardware. And the idea of tensorization is trying to mix and match these two things, and by able to allow the high-level program to translate into the low-level accelerated instruction that's supported by those hardware. Tensorization not only helps us to support new TPU-like accelerators, but it also helps us to support things like Volta GPU, where the Volta Tensor Core Gen is actually something that looks very like the tensor accelerator instructions. So this is a new result that Xu Yan will talk more about today. And that as you might notice that on emerging workload like those that need in transformers, we can get better performance than the native library that NVIDIA provides. Talking about accelerators, one of the most important component of the TVM stack is Vita, which Thierry here worked on. And since last year, we have been moving Vita to Chisel release, which we call Vita 2.0. And there's an exciting new feature coming in. So nowadays, when we're talking about TVM, we talk about how do we optimize machine learning workloads for the current hardware. But there's an even more interesting question to ask, in a sense, given that machine learning hardware is a fast evolving field, how do we go and optimize for our future hardwares that is not even yet taped out? So in TCM last year, we have this new infrastructure, in the TVM last year, we have this new infrastructure of TCM that allows us to directly take a hardware description language such as a Verilog or Chisel, bake that into a Verilator and directly connect that to the TVM runtime. That means that we can do end-to-end hardware co-simulation and use AutoTVM to optimize your machine learning program even before your hardware tape out. And we believe this is a very exciting feature, and that's something that we are looking forward the community to collaborate on and pushing forward. Okay, so far I've been touched on a few points about the community's major focus in the last year. Let me talk a bit about where we are going. Of course, this by no means a non-comprehensive topic, so I'm only talking about something that I think that are going to be important. So the first thing is that as we are starting to see machine learning deployed into more devices, we are starting to see a huge wide spectrum of runtimes and devices that want to deploy. This might include being able to integrate my runtime into certain NPU drivers such as Hexagon or other ARMS NPU or Edge GPU or other devices. It might also mean integrating certain runtime into external runtimes when user needs them. For example, TensorRT or fallback into TensorFlow runtime when some operator is not supported by TVM. We want to try to build a unified runtime interface in the TVM runtime that allows us to expose all those different runtimes in the same interface. The idea is that by subclassing all those runtime modules into what we call TVM runtime module and exposing a limited set of functions, including a get function that gives you the packed function protocol that TVM support, as well as the binary serialization format, allows us to be able to build a runtime that allows us to package and export all those machine learning runtimes in a single interface. So by using a unified runtime, we'll be able to have a composed module exported to a single shared library, load that from any of your front end, including Python, JavaScript, Java, and Go, and also give you automatic support for all the benefit that TVM runtime gives you, such as RPC support for remote profilings and auto-tuning. The second thing that community is actively pushing on is actually improving our IRs. So as you heard from Zach today, so we have a new IR effort called Relay that's a high-level functional IR, and historically we also inherited IR from Halide for low-level code optimizations. And there's effort on trying to rethink how we can co-design the IR together to build a unified IR structure that can benefit both the high-level and low-level optimizations. This is still a very early stage, but at a high level, what we want a unified module that can give us different functional variants. So a function could be a relay function that have a high-level graph, but that function is also be able to call into a low-level, what we call TE function, that allows us to do low-level scheduling optimizations. By having a unified IR, it gives us several benefits. First of all, it will simplify the general compilation flow. So under a new flow, there will be two major functional variants, so we can just import high-level models into an IR module that are mainly relay function, and then doing high-level optimizations there, lower that to a low-level function that could be a TE function, which is a new low-level tensor IR, or external function that can be optimized by external compiler, and we can do auto-schedule on that IR, and then CodeGen phase will hand a middle-level IR module onto a runtime module that we can then go and deploy. There are certain benefits on mixing different functional variants in the same IR. For example, in the same module. For example, we could define a relay function that calls into those low-level functions and still being able to do some co-optimizations across the function boundary. One of the major things that I actually want to investigate on is actually improving the accessibility of TVM. This is one of the lessons we learned from major different frameworks like PyTorch, in the sense that by enabling more people to be able to use machine learning frameworks, and in this case, machine learning compiler framework, we will be able to increase the rate of innovation. The reason is that the area of machine learning compiler research is still a wide open field, and we believe that the most important thing is trying to allow more people to innovate faster. That's why we want to bring first-class Python support to our new IR, unified IR infrastructure. The idea is that for every IR that you can express in a TVM, will allow you to express a Python dialect called hybrid script that can directly correspond as a secondary text format for the Python IR. And you will be able to directly write passes and manipulate IR data structures in Python. The reason is that will allow us to easily accelerate innovations, including interrogating your favorite machine learning method for doing auto scheduling, and by no means we want to stick to Python. So when your method is product ready, we allow you to easily shift to C++ and push a button to be able to build a more robust compiler that can be reused across the languages. One of the major things they want to do is want to rethink the low-level IR structure. There are several things we want to do, including transforming the current way of transformation to use low-level function as a basic element of transformations, and making schedule transformations as optimization passes, and bringing better tensorization support. Another thing they want to be able to enable is trying to think about how we can interpolate with other open source ecosystem. TVM is an open source project, and one of the most important things of open source projects is we can try to leverage what existing open source ecosystem brings us. This includes trying to be able to make use of existing ecosystem like LLVM, and trying to build interpolations from existing IRs into our version of IR, including things like TorchScript or the MLR TensorFlow variants. And we will also try to include an external function packaging mechanism that allows us to introduce external IRs as a component in the TVM IR module. So that allows us to do better customized packaging and better customized code gen that allows us to combine those modules together. Last but not least, automation is always in a fundamental piece of TVM. We always want to try to improve this component. Currently, most of the TVM automation focuses on the low-level IR optimization in terms of auto TVM. We want to enlarge that into across the stack by enabling automation not only for the low-level IR, but also for the backend component as well as the high-level optimization such as automatic quantization, layout, and other things, and combine these optimization with the low-level optimization. These are a lot of things they want to work on, and we are going to spend a lot of effort collectively as a community to work on these points in the incoming year. Of course, this is not by no means a comprehensive list, and there are a lot of other exciting things that the community is going to work on, and many you are going to hear many of them giving talks today. So finally, I want to give a few highlights about the community growth. So TVM, we have been incubating as the Apache TVM for around a year now. And as Louis said, one of the most important things about Apache is this open independent governance that not only allows us to open source code and share the source code, it also means that we want to open development, which means that all the development activities in TVM are publicly available. The RFCs and discussions are available in the Discuss forum and mail list, so that anyone who wants to join the development can jump into the community and collaborate. And finally, and most important thing that brings by Apache community is open governance. That means that whoever contributes heavily to TVM will be granted as a committership and being able to jointly lead the community together. You will hear about many talks from our committers and TMC members today, and we're really looking forward to welcoming you as a part of the community. And in terms of growth, Luis already mentioned that we are getting 70% growth since last TVM conference. That hopefully we can keep that growth rate. And every month there are more than 50 authors contributing over 140 PRs, and there are more than 1,000 forum posts. So I would say the community is really growing, and it's a really exciting time to join. So with that, I will pass the token to Luis to introduce you to the rest part of the program. Thank you.
All right, thank you. All right. Well, with that, I'd love to thank the sample sponsors. A lot of the work that is done in the research side at UW is being generally supported by several, both from sponsors from academia and industry. And notice that there's some space in this slide here in case you're interested in sponsoring us. You can fit more logos there. But all right, with that, let me just tell you how the rest of the day is going to go. So we're going to have now two 20-minute talks on going deeper on how TVM is being used at AWS from Ida and G, and then TVM at Facebook by Andrew Tulloch and Bram Wassi. And then we're going to have a break before we talk about compilers and VMs. Okay. With that, I'm going to contact switch to Ida and G as the next speaker. So thank you. By the way, in case, just a couple logistics. There's bathrooms in that corner right there. Also, there's water bottles there. There's fountains that make it easy for you to reuse your water bottle. And also, if you were speaking, make sure you use a microphone so our friends on YouTube streaming and recording would actually capture the audio. All right. Cool. Let me just go back here.
Give people 1 minute to settle. It's okay. I just give people 1 minute to settle. It's okay.
Okay, so it's really a pleasure to introduce Ida back on stage to go deeper on TVM at AWS. So thank you.
Thank you. Hello, everyone, again. So I'm Ida. So I would like to discuss with you about the deep learning compiler project at AWS together with my colleague G. So First, let me bring the first slide basically of my keynote back with some more details. So this is a reduced snapshot of what we are doing at AWS AI. So as I told you that there are 3 levels, and I just try to expand it a little bit, but this is still reduced snapshot because due to for the sake of space. If you are interested in the complete picture, please refer to our CEO Andy Jassi's keynote in reInvent delivered earlier this week. So as you can tell from this snapshot, performance is really important. So imagine that if we are able to use some deep learning compiler, like in this case we choose TVM, to optimize the performance from the bottom, like on different kind of hardwares for different kind of frameworks, then consequently we'll be able to do better on the second level and ultimately also better on the third level in the AI services. So deep learning compiler is really important to us. As I just said, the AWS choice of deep learning compiler is TVM. And because this is a TVM developer conference, I'm going to skip all the introduction about what's TVM, and I'm going to overwhelm you by this. So this is basically something that we are doing in AWS. This might not be the complete list. I try to summarize the things. So you can see that we do from training to inference, we do from dense to sparsity, we do all kinds of optimizations from graph to tensor, so on and so forth. And we also do accelerator. And on top of those, all the components, we are also building a service called SageMaker Neo. And we run the things like using we run the service using all the techniques that I provided here. And I remember that last year in my talk, I kicked off my talk with a slide of portraits of all our team members. Today, I'm not able to do that because we do not have enough space. So meaning that our team is growing. And also, just a spoiler, so the very last slide of the very last item of the very last slide, we are going to say we are hiring. So if you are interested, come to talk to us. The last thing about this slide is the silly color coding. So the blue color here means that we would cover in this tech session, and the orange color means that we have colleagues who cover in the rest of today, and the red ones is basically we do not discuss in the presentation, but feel free to come to us if you are interested in anything. Okay, so the first part I would like to talk about is QNN dialect. So this is mostly done by my colleague Animis Jen. So unfortunately, he will not be able to make it today because he went back to India for getting married. So he managed to convince me that his wedding ceremony is a little bit important, more important than this. So now I come to present on behalf of him. So first thing that I want to put here up front is like we are talking about consuming and processing a pre-quantized model, meaning that this model is already quantized. We just want to use TVM to consume it, to compile it, to run it. So high-level system design. There are 2 options that we can do. One is we can just completely add new operators from scratch. This might not be good from the system perspective because you are reinventing a lot of things from scratch and you are not going to reuse anything that is already provided by the amazing TVM software stack. So we go with the second option, which means that we will try to define a dialect called QNN or quantized neural network to encapsulate the work that we are doing, and then we can try to reuse all the relay passes and the low-level optimizations that the TVM stack already provides. So this is much better than you reinvent everything from scratch, right? So what is the QNN dialect? It basically is a set of operators that you can easily correspond to many framework quantized operators like quantized, like conv2d, so on and so forth. And in the QNN dialect, we would lower those QNN operators into a number of relay operators. So then after that, we can enjoy all the benefits that provided by the original TVM stack. So just give you some quick example, like this is the QNN quantize. So given the data type, given a 0 point, I'm not going to talk about anything about quantization here. I'm just assuming that you are somewhat familiar with what quantization is. So given the data type, given the 0 point, given the scale, we will be able to we then would define this QNN quantize operator and lower it into a bunch of like divide, round, cast, this like vanilla relay operators, so that we'll be able to process. And another example is the conv2d. So if you give us all the like output data type, also the 0 point and the kernel 0 point information, we can lower this QNN operator into a bunch of relay operators again. And note that this is an asymmetric quantization. If you have a 0.0, then all the operators after this nn.conv2d could be eliminated. Okay, so this is basically the idea of doing a QNN dialect. So we have some preliminary result to do as a proof of concept. We consume a bunch of TF-Lite models into TVM and round it. So you can see we get some reasonable speed up here. The metric you want to pay attention is like we do batch size equals 1. And also, I do not put it here, but I just want to guarantee you that we get comparable accuracy than the floating point 32 models. And this is also, again, a asymmetric quantization. If you do it in a symmetric way, we can get much better speed up, as I just showed you that a lot of computations could be eliminated. Okay, so this is the QNN dialect so far. How can we make it better? So if you look into this workflow, that what we want to do is we want to consume a pre-quantized model using QNN dialect and do some specific QNN paths, and then use the existing relay and TVM workflow to run it. So the component that with a green check is something that we have already done, and the yellow one, MXNet model to QNN dialect, is something that work in progress. And you see that a lot of other things is not done here. For example, like a lot of like layout related optimization that we haven't done, which means that if we can do it, we can get even better performance speed up, showed on the last slide. And also, we only run it on the x86 CPUs. So how about other devices, platforms? That would be also important and interesting to do. So if you are interested, we are very eager to work with you on those components that is not done yet, and together we can make it better. Okay, so this is about the QNN dialect. The next thing I would like to share with you is about two new Amazon EC2 instances we just launched this week. So this, and then how we use TVM to make it better. So this is a work like done by Hongbin, Yizhi, and Haichen. Like 3 of them are, I think, in this room, and a lot of people from Annapurna Labs. So this is a company, the Israel chip company. Annapurna Labs is an Israel chip company that we acquired like a few years ago. So the first instance that I would like to talk about is the Amazon EC2 Inf1 instance. So this is powered by AWS Inferentia. This AWS Inferentia is an in-house chip for machine learning inference that we built in the past few years. So using this instance, we will be able to enjoy lower latency, higher throughput, and lower cost performance compared to another instance called G4, which is powered by NVIDIA Tesla T4 GPU. So in this instance, we can get up to 2,000 terops at sub-millisecond latency, and this instance is it's integrated with all popular machine learning frameworks like TensorFlow, like PyTorch, and like MXNet. So anyone want to guess why we can integrate with those frameworks? It's through Relay. So this is about the instance itself, and then the chip, a little bit about the Inferentia chip. So First, I'm not going to dive into too much details, but feel free to come to me if you have questions or interested in knowing more. So first, we have 4 neural cores per chip. So because of this, we need to do a lot of customized tensor level optimization to make full use of this chip. Secondly, in the chip, we have 2-stage memory hierarchy. We have large on-chip cache, and we also have a commodity. We also have commodity DRAM. So then, obviously, we need to very carefully and proactively manage the data movement between different kind of memories to enjoy the provided compute power. And third, we have a fast chip-to-chip interconnect between chips, like via some specialized communication protocol. So because of this, we are able to do some model parallelism in pipeline. So it's basically some kind of pipeline parallelism so that we can increase the throughput of the machine learning inference without losing much latency. Okay, so this is the first instance, the EC2 instance that I would like to share with you. The second one, we called it Amazon EC2 M6G, R6G, and C6G instances. This is powered by ARM-based CPUs. It's also in-house ARM-based CPUs called AWS Graviton 2. So as the name suggests, there's a AWS Graviton processor that we launched last year. So compared to that, we get much better performance in terms of compute power, the memory capacity, and the overall performance. And also compared to the current x86-based instances, we get better price per performance in this price advantage. So in this Graviton 2 processor is a general purpose CPU, so we run a lot of general purpose benchmark on top of it, like spec, like memcached, to show that it's powerful. But we also want to run machine learning inference on top of it. So the first thing I want to say is general purpose CPU is also capable of doing machine learning or deep learning inference, and actually a lot of inference jobs happening on the general purpose CPUs. And in our ATC 19 paper, we show that you are able to run machine learning, like CNN model inference, very efficiently on this kind of a general purpose CPU. So compared to M5, which is powered by x86 CPUs, M6G actually does faster machine model inference with lower price. Note that this is absolute better performance, not price per performance. So in order to do this, we are using TVM to lower the model all the way to the using the ARM Neon instruction, and we actually all the way go to the assembly level to look into the assembly code of those computationally intensive kernel to make sure that we are fully utilizing the computation power provided by this CPU. Okay, so this is about the ARM-based new CPU instance that we just launched. So the last thing I would like to talk about before handing over to my colleague Zhi is about a tutorial. So just now, Luis said that we spent a lot of time this year to improve the tutorial, and I was also part of the effort. I was in the FCRC tutorial as well, but unfortunately, I still think that it's not enough. Why is that? So check this out. So this is a typical conversation that happened to us and maybe to you as well. So we have customers, users, or new hires who are new to this field, and they come to us, ask questions, something like how to use TVM to do something. TVM is very powerful, so you can do this, do that, right? So a lot of things they can do, but using TVM, but how to do that? So they come to us. So we are very passionate. Well, some people would like to use TVM, so definitely you can do the following. Step 1, step 2, step 3 is never going to be easy. So then the customer, the user may say, wow, cool, meaning that it's too complicated, I cannot remember. So is there any tutorial? Of course, we do have tutorial, right? So I said, yeah, check this out, and check this for this, check that for that, because our tutorial is kind of fragmented, like it's everywhere. So just do this, and this kind of like conversation would just, you can iterate. And eventually they may come to us and say, I failed. TVM is really, really hard to get started. to use, to deploy that phase, they are frustrated. We are frustrated. So, and also the other evidence that I just try to collect a little bit from the discussed forum is like you see, a lot of like thread talking about some like easy stuff like how to start to use relay confused with some very easy entry-level function, and there's no speed up, and is there any beginner guide to contribute something like this? So, which makes us think that maybe we need to come up with some more systematic tutorial. So luckily, we have some this kind of experience before. So my colleagues, Alex, Aston, Jack, and Mu, so they, 4 of them, like in the past few years, they wrote a book. It's an open source book called Dive into Deep Learning. So this book is an interactive deep learning book with code, with math and discussion, so that you can run it. It's totally open on GitHub. You can run it on your laptop in the Jupyter network notebook fashion, and it's presented in multiple languages. And in Chinese, there's already a book. It's a #1 bestseller online, and the English version is also available during reInvent, and it's going to be, if you guys happen to go to Vancouver for New Year's next week, it's going to be available there as well. So this book is very successful. You have so many stars, and also we get good adoption. A bunch of top universities. We just list a few names here, like those. Check out the map. So they are using this book to teach the deep learning course. So this is what we have done, and we are thinking about if we can extend this part of this kind of work to the deep learning compiler side. So here is the deep learning D2L compiler effort that we are putting together, but it's very preliminary. Let me show you something. So what we want to do is we want to provide a systematic tutorial for the beginners who want to use TVM. I highlight the use here, so it's not for you. It's not for the people who would like to be a developer of TVM. It's just for people who want to use TVM. And more broadly, we want to make it as like to those people in general who would like to take the Deep Learning Compiler 101 class. So this is the goal. And inherited from the D2L book, we would like to make it as a Python notebook fashion. So it's runnable on your laptop. And in this case, maybe Colab, because we need to use we need to use GPU to show something, or maybe even other platform. So you want to run it online, and obviously we will make it available on the EC2 instances that you can use. And the very preliminary point 1 is already released. There are 22 sections just covering very basic stuff from getting started, how to install TVM, how to get your hand dirty to do some very quick thing, and some basic operator level optimization. So it's far, far away from enough. And so we call for contributors. So the point here is like, we are hoping that if anyone are interested in doing this kind of things, please join us. It's going to be open source, and you are not going to get money from it, but you are going to be able to help people. And but heads up here is like, based on the experience that we had for D2L, this, if you commit to it, this is going to be very time consuming. But if you're interested, just come to talk to me, like any point. So with that, I would hand over to my colleague Ji. Thank you. Or maybe we can save the question
At
later.
the end? Okay,
Yeah.
sounds good.
Okay, my name is Z. I'm gonna talk something more later. As Ida just covered some TVM related work that we've been doing at Amazon, and I'm gonna talk about the Neo, the high level picture of Neo, and also I'm gonna talk 2 more projects or works we've been doing at Amazon for TVM, and one of them is still actively working on, and the other one has been merged. So let's first talk about SageMaker Neo. Okay, So the goal of Neo is to like enable customers to do model training once, and then we can run it anywhere. So Neo currently takes like different inputs. Like we can take algorithms from SageMaker, and these algorithms are like some traditional machine learning algorithms, and we can also take some models pre-trained from like popular frameworks, and also we can take the models from XGBoost. And then SageMake Neo will like take these inputs and then we do compilation and also optimizations. After the optimization is done, we can then deploy the models, compiled models on various hardware targets like ARM, Cadence, Intel, NVIDIA, RISC-V, and Xilinx. I think TVM can do like most of this work as well because sitting in the heart of Neo is TVM. And another good thing is that for SageMake Neo, we enable users to have like a very quick one-click compilation so that we can help users to simplify the efforts for model compilation and also deployment. Okay, so this is the like compilation flow for Neo service. A customer comes to Neo and they can like have they can open like the SageMake console page. Then they want to bring their own models. These models could be trained by SageMake as well. And also they want to have like some compilation configurations. Like you want to compile it for a certain target, or you want to compile a certain model with a certain input. And also something like you want to, like after the compilation, you want to store your model somewhere in S3 bucket. So with these configurations, then you can start to click on the compilation button and then to initialize the compilation job. Then after the compilation is done, then you will like have the artifacts for TVM will have 3 artifacts. One is the SO file, and one is the primes file, and also another one is the JSON, right? And we take these like 3 files. Of course, for other objects or for other models like XGBoost, we may have different artifacts. Then we save them somewhere into S3 buckets as you specified before. And later on, the customers can directly download these compiled models, and they can take them to deploy by themselves anywhere on the specified target. Also, you can also launch some like endpoints to initiate the doc image for inference in the cloud. So this is the major compilation flow. Of course, there's also a lot of service related work in Amazon EC2 instance. So we are not going to talk about it here. And also, SageMake Neo forks TVM, and we also contribute our code back to the community. And so Neo is an open source project that is designed to be a multi-vendor project with every participating organization grant ownership in the project's governance. We look forward to work with like device vendors, also hardware processors, and also academic labs to help them to bring their own compilation toolchains, also like the runtime into TVM. Sitting back in the TVM, there's a deep learning runtime, which is called DLR, which is also open sourced. And it has a bunch of runtimes in it. Like we have TVM runtime, we have like Treelight for XGBoost. Also, we have like some other runtimes like TFLite, so that we can have better model coverage and also model coverage. So if we are also talking to other like vendors or like accelerator makers to bring their own runtime to the DLR part, so that they can have a Neo contrib runtime to initialize to have better model coverage. So there's another way that you can bring your runtime to like Neo. This is something we encourage. So we encourage the users or like the hardware vendors to bring their own codegen tool to TVM, so that we can have like a contrib compiler on the TVM stack and then we can have the TVM to generate artifacts that could be compatible to the TVM runtime, so that we can initialize it and also launch it later, which is pretty convenient for the users and the customers. Okay, that brings it to this topic: bring your own torching to TVM. This work still being like actively working on. Like Cody and I are working on it, and Jared also have the prototype in the very beginning stage. So let's take a look at why we want this. So suppose you are a vendor, and you are making some processors or like accelerators. And these accelerators, they work very well on some like popular models or like popular operators like Comp2D, like Maxpool, ReLU, this kind of operators. But one day, even for these operators, these limited operators, you may have covered a large body of models, like from image classification models, right, ResNet 50, this kind of things. But as there more and more models emerging every day, and you probably one day you will like have some models that you cannot support because you have some operators you cannot support by your hardware. Like if you come to SSD models, you may have some operators like non-maximum separation. These operators, they have control flow, like they have like some complicated control logic in it. So this is something you cannot support by your device, but you can do something very expensively. Like you can like redesign your hardware, or you can like have some special handling for these operators, right, to make it work. But these are very costly. To this end, TVM is going to be your good friend, because we can ask TVM to like do some fancy work for you. So you can ask TVM to like make your whole graph or like a relay program into some segments. So some of them you can like just offload to your hardware or your device, and you can leave TVM to do code generation for the part that you cannot do. And so intrinsically, so you will have like TVM to take care of the operators you cannot support, or like the part of the network you cannot support, and you can like have the backbone network like ResNet 50 still run on your device. So this is the high-level idea why we need this. And then let's take a look at how TVM would look like after we integrating this thing to the TVM stack. So on the top of this graph, you'll see we still have the relay program, and then we still have the like some original program that converted from some hardware, like some parsers or like some front-end frameworks. And later on, instead of running some like optimizations or compilation directly, we're going to have an extra step, which is to annotate your program and also partition it into like different segments. And these two passes could be transparent to users. Like they can just provide a list of operators using a template we're going to provide. And also, users can do some also like more complicated work. Like they can annotate the program by themselves, which like by writing some passes to do this. And this is a little more complicated than, but anyways, then by doing this, you have like a partitioned program. And then you can send this partitioned program for optimization and also compilation as the usual process we do in TVM. And then later on, in the compilation or like the optimization, we have to invoke different code-gen tools, right? So previously, we only have like LLVM, CUDA, this kind of torching in TVM. Now you may bring your own torching at this layer. And then we can largely reuse some kind of TVM code to do like serialization and this job for you. So it also easy your work here. And then after this code is done, we can take this like a blob together and send it to TVM runtime for execution. Sometimes you may need your own runtime, like for TensorRT or like for DNNL, they may have like an execution engine. But we can make them compatible somehow to TVM, then we can invoke it directly from the TVM runtime, right? Or sometimes you don't even need to have a runtime engine, and you can probably just have like a a DSO file or like a C wrapper, which could be linked or compiled together with TVM runtime. So that's very convenient. So that's what you are going to do essentially. So because we are going to take care of the front-end part, like the partitioning, the annotation for you. So the most of the work you want to do is to have your code gen tools and runtime integrated into TVM. So depends on the application or your use case. You may have to. So sometimes if you have the engine, just as I mentioned a little before, you need to generate like a artifact that can be lowered or saved through TVM runtime module, and then we can lay down invoke it directly. Or if you don't have an engine, you can just produce like a C source code, which is a wrapper for your API, and then these are compatible to TVM code. So the good thing here is that you don't need to expose your IP directly to anything. You just need to provide some APIs and the wrappers to access it and also to invoke it. And for the runtime, most likely we can reuse most of the TVM runtime logic. And you need to customize some kind of runtime, like if you have a JSON file, you want to have an interpreter for the JSON, which is pretty simple to write, and it's also pretty thin layer. And then you can invoke it directly through packed functions. Okay, so that's the other work we've been doing, like in TVM, which is the pass manager. We know that as Relay is featured with like a bunch of, not even a bunch, probably dozens of optimization passes, and how to orchestrate these passes and systematically manage them is actually challenging, because otherwise, a pass developer would have to spend a lot of time to figure out how to apply them correctly or something like that, right? So this motivates us to have a systematic way to manage these passes in TVM or in Relay somehow. And this could be even extended to lay down if we have unified IR, right, for the TVM IR. So we take some advantages from traditional compilers and also deep learning frameworks. In the traditional compiler like LLVM, it has also a pass manager. The job of the pass manager is to do the following work. Like we can have this pass manager to, it makes the pass developers' life a little easier, because the pass writers is going to just focus on the skeleton of this pass, and they can rely on the pass manager to resolve the to apply on each granularity of the program. And also, the pass manager is used to maintain some pass information, like the dependencies between passes, so that the dependency could be automatically resolved. And it also keeps some information up to date, so that you don't need to reapply some passes if you don't change the program states. And in the deep learning framework, we also have some similar ideas, like for PyTorch and Keras, they have sequential, and like for Gluon, they have block. It is used to help the developers to stack a bunch of layers together, and then you can use a bunch of them to build up a large model. So this allows a very flexible, customized pipeline. So we take the ideas from here, and also we want to build it in the in Relay as a pass manager, so that we can have the advantages of both the traditional compiler and also the deep learning framework, constructs like Screenshot. And this is how it works here. So, so we have a Relay program which is converted from front-end parsers, and then we have the compilation flow here. Then we take this program for optimization and use pass manager. So depending on what you want to optimize, there might be some different granularity you can apply on. So the first one is like a module pass. It means you want to write some optimization that probably needs some global information from the whole module. Like you want to add a program, or you want to delete the program in the module. For example, we have some passes like lambda lifting or inline, this kind of passes. You may need the whole global information. Or you probably just want to add or remove some expressions in a function. In this case, you just need the local information in the program, in the function. And then you can rely on this. You can just have a skeleton of this pass, and you can rely on the pass manager to apply it for each pass in the whole module. So some of the examples are like Fusion, cost funding, this kind of things. And build upon these two passes, or these two types of passes, we can have like sequential passes, which is going to help you to apply on like a sequence of passes. And this is going to help you to optimize your own customized pipeline. And we can have an example here. Oh, pipeline, yes. And with this optimized passes, you can then apply the optimized program and take it to the relay runtime. So this is the example. Like you can have different passes, and you can use different configuration file to configurations to apply for it, and you will have the optimized model. And in the we also have a tutorial here for more details. Please go to that one. So the following are the talks for the rest of the day from Amazon. So Haichen is going to talk about some dynamic execution and the virtual machine. And Yao is going to talk about dynamic models with graph dispatching. And also Cody is going to share some ideas about improving AutoTVM efficiency by schedule sharings. And Yue is going to talk about optimized bus and graph kernels through TVM. And there's some takeaways. So first, industry needs an open standard compiler for DL, and Amazon is actively working on TVM stack for this. And we are eager to collaborate with the community, and you can talk to us and grab some of us. They are sitting over there. We have around 10 people join here, and probably here as well. And the last but not the least, we're hiring. Yeah, again. Yeah, please just write to either me or our managers, Vin. You can also talk to us offline. Thank you. With that, I'm happy to take any questions.
Do you have any questions for Ida or Chi before we contact switch to Facebook? Questions? No? Okay. All right, so while we contact switch, maybe see somebody warm up. So keep, yeah. You still have one more minute to ask questions if you, while you contact switch here.
Or you can just come to us later offline.
Okay, all right. Thank you guys again. All right. Cool. All right, now we had everything yellow with AWS, everything blue with Facebook, right? Thank you for coming. Andrew and
Brown.
Both Brown.
Wonderful.
This is the newest version. So, everything okay there?
It looks good.
Yeah. Great. There's a clicker here, and make sure you guys use the microphone so it gets recorded.
Okay, okay.
All good?
This one will just be
Both of them are wired, so.
okay.
Thank you guys for coming again. All right.
Excellent.
Hi, everyone. It's really great to be here. As a lot of the other presenters have said, you know, in the past year, there's just been this huge growth in the TVM community. And yeah, it's really exciting. So at Facebook, we've been contributing to TVM for the past year and a half or so. And yeah, it's just been a really awesome experience. So I'm presenting here with my colleague Bram, and I'm going to talk about sort of TVM for machine learning systems at Facebook, and sort of talk about sort of an end-to-end, you know, example of how TVM and sort of model system co-design was really helpful in shipping one of our new sort of speech synthesis models. Bram's going to talk about sparsity and sort of modern deep learning models, and talk about PyTorch JIT and the TVM integration we've done there. Later this afternoon, Anshu and Hal, my other colleagues from Facebook, are going to talk about applying TVM in our ads ranking stack. So with that, I want to sort of give some context for sort of how at least I and a couple others think about TVM for machine learning systems. So broadly speaking, 5 years ago, when I started working on deep learning, we were using these tools like Theano or Caffe or LuaTorch. These systems were a lot simpler and probably a lot easier to use, I think, or at least a lot easier to implement. We mostly cared about these old Tesla GPUs, these Kepler generation. We had fairly static and limited control flow and sort of computational patterns. And performance was pretty far from the roofline, as the jumps that we got from cuDNN and MKLDNN and so on existing hardware showed. There are lots of sort of easy Pareto efficient improvements we could make to our models and our systems. But the world looks really different today, right? We have so many more applications and so many more domains we care about. The low-hanging fruits in our compiler stacks have been increasingly been picked. We have so many more targets. We just heard about a 2 petaflop system from AWS, and we're also hearing about and using these sort of very low power 100 megaflop and 10 megaflop embedded devices. And so as our applications become even more pervasive and real-time, everything from CV to ASR to MT to TTS and so on, our models are also becoming far more demanding of our frameworks. Through tools like architecture search and so on, we really directly optimize for the machine roofline in a lot of cases. And so achieving roofline for a wide diversity of models matters a lot more. And so that's, I think, a really key feature of the TVM and the compiler stack, echoing what we've heard before, that achieving peak performance across a whole range of architectures is arguably impossible to do without this compiler technology. So at Facebook specifically, we still see a sort of a huge demand for flexibility, portability, and performance. So taking PyTorch specifically, one of the main framework we use at Facebook, it's far less constrained and more expressive than previous frameworks, which is awesome from a developer experience, but introduces a lot more challenges on the ML backend side. So we have conceptually, between 500 and 1,000 tensor operations in the PyTorch tensor library, which makes porting it to new backends and enabling new hardware even more challenging. There's a huge set of programs that users construct and a huge range of platforms that we want to deploy on. And achieving close to roofline performance for this diversity of hardware is a real challenge. So I want to go through a sort of end-to-end example from earlier this year of a real-world production application where TVM was a really important part in sort of the whole stack. So I think this helps demonstrate a bunch of a nice application of the TVM stack. Might convince some of the haters and skeptics in the audience, but it also touches on some tricks like sparsity and so on, which Bram's going to go into more detail. So the domain here is speech synthesis, or TTS. So in the last few years, since, say, WaveNet, WaveRNN, and so on, these neural autoregressive models have displaced previous approaches for state-of-the-art. So the high-level block diagram looks a bit like this on the right. We have our acoustic model, which generates features from the text, and then we have this autoregressive net, which generates the sample waveform. So the autoregressive part here means that we have this strict sequential dependency where the output of the model at time t is fed back as an input at time t+1. So similar to challenges with scaling up like distributed synchronous SGD, the latency constraint due to the sequential nature of the problem is a real challenge, particularly in the speech domain where we're generally sampling at, say, 24,000 samples a second, which is an implied latency of about 40 micros. For folks familiar with stuff like, say, standard ResNets on CPUs or GPUs, this is about a couple orders of magnitude smaller. So taking a WaveRNN style model as an exemplar. So this is about a year old. How this works is that we feed our acoustic features into a stack of RNNs, then some fully connected layers, and then we sample from the softmax. So earlier this team, one of our groups at Facebook had built an incredible sounding synthesizer that we really wanted to ship to replace our existing stack. But the latency challenges in this model were insane. Nearly 2 orders of magnitude off where we needed to be. So even sort of a back of the envelope speed of light analysis, assuming we use all our arithmetic units on our hardware, we still wouldn't be able to get there. So this was a real challenge. But the sort of approaching this from a sort of joint software hardware modeling perspective was really powerful. And so I'll just step through a couple of layers in the stack where we use TVM. So there's a couple of obvious low-hanging fruit here. So the first is getting rid of the framework overheads. So in our typical machine learning frameworks, every operator you execute, every function call, has some overhead which the framework introduces. So this is typically in the orders of hundreds of nanoseconds to a microsecond or two. So given this sort of 20 microsecond budget and half a dozen or a dozen ops, we'd be spending our entire overhead just on the framework itself. So whole graph compilation with tools like Relay is a really great answer to this. So given this problem has entirely static shapes and a static data flow, we can almost entirely eliminate the overhead using the existing TVM graph runtime. So the other area where whole graph compilation is incredibly beneficial right off the bat is through operator fusion, as we've heard before. So given this sampling operates at batch size 1, almost all our operators are memory bandwidth bound. So all the fusion examples are incredibly efficient here. The optimized code generation for stuff like GemV is also incredibly helpful here. But this helps, 10, 20%, and there's a whole bunch more to go. So the next direction to look in is this sort of model software co-design and stuff like sparsity. So sparsity is helpful for a couple of reasons, both important in this application. So it reduces the number of flops executed, which given our sort of previous speed of light analysis, makes this problem a lot more approachable. The second area where it helps a lot is reducing the cache footprint of these models. Since we reduce the size of our weight matrices, which dominate the cache footprint. Why this helps a lot in this case is that it allows us to keep our models resident entirely in stuff like L1 or across the per core L1 or L2 data caches on our CPUs, which is incredibly important to avoid expensive reads from L3 or main memory. Generally speaking, block sparsity and sort of structured and unstructured sparsity we think is incredibly important, and it's like going to be a really dominant feature. I imagine we'll hear a lot more about it this afternoon from AWS, and we'll also hear a lot more about it next year. It's becoming, I think it's a really big opportunity for a lot of our ML systems and our ML compilers to take advantage of these. And we can go further with tools like reduced precision storage for our weights as well. Once we go through all this, we end up spending a surprising amount of time in our transcendental computation. So normally, like a lot of the intuition we build up in a bunch of these domains is that our nonlinearities, like ReLU, sigmoid, swish, and so on, are pretty trivial parts of our computation. But once we optimize the dense math and so on, we end up spending a lot of time here. So in a lot of backends with TVM, we end up invoking external functions, like in libc and so on, for our transcendental functions. And so what we really want, we spend a lot of time here. These aren't cleanly vectorized. We might spend a bunch of time in, say, very high precision polynomial evaluation or a bunch of conditionals. And so what we really want is to express this entirely in TVM-AR and fuse it, vectorize it, and so on entirely. So with a couple of modifications to Relay, we're able to express these kind of approximations. And not only that, by expressing them purely in Relay, we can also optimize the polynomial degrees and coefficients with tools like Solya to allow us to trade off performance accuracy. So putting it all together, this is actually a pretty small project in the scheme of things. We build a couple of new Relay primitives for sparsity and so on. We add a couple of lines into Relay and TVM to express these new primitives. We introduce a few knobs for the TVM multi-threading runtime. We use work in tools like AutoTVM to guide our architecture search. And we can do all this in a couple of days, which is an incredibly productive tool chain. And so sort of the end-to-end results look something like this, where we start out with this very high latency model, and we can apply whole graph compilation, apply unstructured sparsity, then structured sparsity, reduce the precision of our storage, and then approximate our transcendentals, and zooming in just to see the really relevant part of the graph. We can see how all these optimizations stack together. So really, this is a really pretty great result for us. We're able to ship it. And not only that, we can do this without a single line of architecture-specific code. So we can validate this against alternative approaches, such as just hand implementing the whole thing in C or assembly intrinsics. And we can beat that by substantial margins on held-out architectures, so to speak. Another nice thing, because of the sort of portability of TVM, is that we get real-time on mobile for free. So we can apply this with modified architectures on modified platforms, reuse 99% of the code. And so this is a really great case where we can deliver on the sort of promises of performance, portability, and generalizability. So with that, I'll hand over to Bram to talk about the use of sparsity in sort of modern deep learning compilers. Thanks.
Hi, I'm Bram, and I'm just going to be talking kind of about some research ideas and just things that we're interested in at Facebook with regard to sparsity, and then I'm going to switch gears and talk about PyTorch integration of TVM on kind of more of like a programming languages front. So sparsity has been around forever. L1 regularization kind of naturally leads to this. It's almost an artifact that you get for free. But in the past, I think it was mostly used for accuracy. You weren't really getting any performance opportunities from it. But what we found is that during inference time, sparsity can actually really, really help your model. There are more complex loss terms you can actually embed into your model that have been solved. And this is actually from a couple years ago. With different optimization techniques, and there's been some success there for convolutional neural nets. There's also some interesting papers coming out these days about sparsity that are a little more complicated than just get as many zeros in the model as possible. There's this Lauder ticket hypothesis coming from, I think, MIT, which basically states that using standard pruning techniques, you can get subnetworks that are just better. You can then reset the weights back to the original values, retrain the model with just that subnetwork, and it trains faster, equally as fast, if not faster, which is a really interesting and kind of non-intuitive result. This just indicates that like sparsity is pretty much something we should be looking into, right? Like you kind of get it for free almost in a lot of these papers. What we found kind of with the Lauder ticket hypothesis is, but MIT found with the Lauder ticket hypothesis has been kind of very influential, and we're kind of continuing along that path at Facebook. But there are other things that you can do to get sparsity in the model. There are two factorization techniques I'd like to talk about, one of which was released by OpenAI for their sparse transformers. They basically kind of factorize the model into, factorize like a dense layer into two sparse layers. So it's like a two-step process. When you multiply by one sparse matrix and then another sparse matrix, you effectively recover all of the connections from that original dense matrix. There's obviously a whole bunch of different types of factorizations. You can explore this link to get like more information on exactly what these two are. But this has been really influential work when it comes to sparse transformers because you can save a lot of flops by having these now easily optimized memory-bound operations. Another interesting bit of factorization techniques that came out is the butterfly matrices. These approximate different types of transformations through kind of sequential sequential applications of sparse matrices. They use a canonical example of FFTs and show how those can actually be factored into, they interpret the FFT as the recursive algorithm and then factor that into repeated application of sparse matrices. They then go on to say, hey, if you can do this with FFTs, you can probably do this with learned transformations, and it's a really nice write-up that I'd highly recommend you check out because you get all of these sparse matrices which can then be used at inference time later or maybe even during training time, and this is the stuff we're interested in at Facebook. So PyTorch has support for a lot of this stuff. We do have a pruning API, as well as a tutorial that hasn't quite been landed yet, but there is a pull request, and I urge you to check these out. There's a whole bunch of techniques that you don't need to rebuild yourself. There's random L1 and even L arbitrary N regularization techniques that you can use to get zeros in your models. But then there's also types of structure that you can induce in the model. Having zeros randomly is not always as kind of useful when it comes to performances, having zeros maybe on certain channels so that one channel just gets eliminated entirely and you can just run things faster, or blocks of kind of values, as we saw with Andrew's work. Block sparsity allows you to get pretty substantial wins. You can then also use your own kind of custom masks. A lot of this work was done by Michela Paganini at Facebook. So let's talk about performance. So we can see here is some work done by Alex Z and Jong-Soo Park. And this is currently written into Asimjit. Doesn't need to be. We could use TVM. This is just kind of a deep dive into why we're getting performance and how that is actually achieved. So what we do is we embed the weights directly into the code. As we can see on kind of in the assembly here, not everything is being FM-added. Kind of like, it seems like almost a random structure of FM adds and broadcasts here. And that's just because what would multiply out to a 0 can just be skipped. You unroll the loops entirely, you eliminate a whole bunch of FM adds and loads, and you get perf from that. Skipping all of these loads and max actually yielded some really interesting results. We saw that with 90% unstructured sparsity, we get a 2.3x win for a batch size 1, 256 by 256 GemV. This is actually a very common size that we were using in a model, so this was really, really nice to see. But if we reduce the sparsity to only 80% and add a bit of structure, we can get substantially better results. This comes from the fact that we're just, loading vectors, and if those loads are contiguous, you can skip more contiguous zeros. It's pretty kind of obvious stuff when you think about it, but not everyone is going to necessarily have that full picture of how do you actually train a model to do this. That actually turns out to be quite hard. So there's a lot of kind of interactions that need to happen between researchers and then also the folks who kind of are targeting certain architectures and know that a width of 8 is preferable to a width of 4, or maybe even a width of 16 is better. We saw that actually you get super linear results here, which is kind of cool because it's 1/5 the number of weights, but because now you're basically an L1 cache, you can do a bit better. We see 70 effective gigaflops over the 11 that we were getting earlier, which, this is on some random CPU, so these numbers are not really representative, but the relative scale here is pretty impressive, which is that it's like 6 times faster, basically for free if you can get a model trained that way. So again, PyTorch has training mechanisms that are kind of plug and play. You can drop these in and train sparse models, so I'd recommend checking that out and then using techniques like this to get the inference speed that you want. So concluding on kind of this idea of sparsity, there's kind of a new interface or interaction that is starting to happen between model developers and then the folks who are writing compilers. Sparsity is pretty easy to achieve and you get the performance, but model developers aren't going to necessarily know how much performance. And this is kind of like a new concept, right? Like the visibility into what is good or what is bad when training a model is now weight dependent rather than just the sizes. So tuning, various hyperparameters there might not actually do much for you. Instead, you're going to have to either figure out regularizers that naturally lead to this kind of, block sparsity, or just manually embed the block sparsity and see if you can train a model from there. This kind of visibility can be solved in a bunch of ways, and there are a lot of ideas about this. Potentially even just putting the performance in the loss function would be kind of interesting. But this is something that I think needs to just happen more frequently. It's like an interaction between folks who are more interested in the research of training models and then talking to and really understanding the implications of those models that are being trained and how fast they could potentially run during inference time. So this is kind of the new challenge, I think, that we're definitely facing at Facebook. So yeah, shifting gears a bit, I'd like to talk about how PyTorch and TVM are being integrated. So this is now going to jump more over to programming languages and kind of how we're doing things at the PyTorch flexibility level and still being able to leverage a lot of the performance wins we get in TVM. So this repository here, PyTorch TVM, lowers TorchScript graphs into Relay. A lot of the work here is done by Qimish Lingyi, Wenchao, and Yinghai. A bunch of others also have contributed. And you'll probably want to check out this blog if you're really interested, which has a little write-up on how this was done. We can see the results are really good. This is a bit old. It's using ResNets, and it's just kind of obvious that if you drop into a substantially faster backend that is compiling things, you get wins. And the way we did this was by using TorchScript. So TorchScript is the kind of static interface to PyTorch where you lower Python directly into an IR that can then be manipulated. But even though you can lower things into an IR that can be manipulated, doesn't mean you can optimize it very easily. It's not fun at all. The workloads being run are not too complicated. you just need maybe a bit of control flow, which is always a great thing to see. But when you have a language that can like change the types of variables and then modify its own functions as they run on the fly, it's really hard to like prove things and then optimize them. So TorchScript was developed to have this portability, but we are trying to get performance from that. And we have two techniques that we're using that I'd like to talk about, in which you can go from like this generic Python runtime into a very fast, kind of much more optimizable interface that we can then lower into Relay, and then let Relay do all its crazy magic and TVM do all its crazy magic to get performance. So the first way that kind of I think a lot of folks have come to the conclusion is an interesting and easy way to get this going is lazy tensors. Instead of executing operations immediately, you just accumulate either like a tape or a graph of the operations and then execute them as late as possible. So at some point you want to execute them, you now have a whole tape or graph which can then be converted into some IR, lowered, compiled, and then if you don't want to compile it again because it's going to be the same workload pretty much every time, you just look it up in a cache. This has proved to be pretty useful. We have a PR up, it's not landed, that doesn't really show all the perf wins because a lot of the stuff's internal, but it does work and you can use it if you are interested in this. There are a lot of limitations though. If you have very weird dynamic graphs that have a ton of control flow, lazy tensors will not capture any of those semantics. You're always going to be recompiling and you're not even getting a perf win at that point, you're just slowing everything down. Similarly, if you're only compiling some of the time, you're going to randomly hit cliffs where, oh, your workload hasn't been compiled before, now everything's slow. So sudden changes and various kind of interesting details with deployment often make lazy tensor not feasible. So instead, we thought of the idea of a profiling executor. Sorry for the graphic on the side not being very informative or even readable, but basically what we're showing is an IR that has inserted guard nodes, and I'll talk about that in a sec. So profiling executor executes everything immediately as you normally would. It's just like PyTorch in terms of its interface, but it's recording everything. So it's accumulating statistics about shapes, constants, d-types, even the different kind of variability of the shapes. So if the leading dimension changes over the course of the program, it'll record that. If the tail dimensions aren't changing, it'll say, hey, this is pretty much static. This information is super useful because then you can write guard nodes or insert guard nodes manipulating the IR that say, hey, I've assumed that most of the time this leading dimension is going to change. This third dimension is always going to remain static, and it's going to be constant. Or sorry, not constant, or else the first dimension would change. It would be like float or something like that. And then if that isn't true, fall back into the interpreter. Do the slow path, whatever, that's okay. But in the case that it is true, we can now optimize a subgraph. And this subgraph can be handed off to Relay, optimized crazy amounts, and then used more frequently than everything else. What we've now isolated is a very common workload that we can then use, control flow and a whole bunch of other things to optimize while still having the flexibility and maintainability that PyTorch offers developers, where in the worst case, you fall into an interpreter, which can still do everything that you're used to. With Python, we found that this is kind of like one of the best ways to actually get perf for the things that we care about. We don't want to hinder researchers who are developing really complicated models and changing functions on the fly. We just want to let them do their thing and still, in the common case, get a lot of performance. There are some downsides. You need to run a couple times before you get performance. So when it comes to deployment, you may want to do like crazy caching things or like ship the pre-compiled version or even ship the pre-transformed version. And then the IR itself is very complicated. If you start dumping these things, as we can see, there's a lot of guard nodes. There's a whole bunch of stuff that you need to analyze. So if you still want to do whole graph optimization, it becomes just almost, it becomes very, very difficult. Not infeasible though. Cool. So couple next steps. We're really excited about the performance of TVM. We've been using it internally for a whole bunch of different things. We're working to more tightly integrate PyTorch and TVM. I think this is going to be a big thing going forward. Like TVM is clearly the way to go. It's got a whole bunch of different abstractions that are, especially the ones based on Halide, very useful and convenient. You can get things done very quickly. As Andrew mentioned earlier, it only takes like a week to get massive performance wins. So we're really excited about that. And I'd like to give a big thanks to the community, Andrew as well, and I guess open up for some questions for the next 5 minutes.
Questions before we break?
Do you think we're headed for a future? So sparsity seems to be very effective. Do you think we're heading for a future where down the line, you would never do anything that's not sparse?
Sorry, never do anything that.
Do you think we're headed for a future where we would never do anything that's not sparse?
I wouldn't say that. today, like quantization is very effective in almost all cases, but still it's not like everything that uses, it's not like we always use quantized models everywhere, or all our hardware only supports quantized models. So I think with that, I'd say it's more like where quantization was, in 2015 or so, before like a bunch of our backends started supporting it as easily, a bunch of our hardware supported it as easily. I think that's more the analogy.
Yeah, I think when it comes to even defining sparsity, I like to think of it more as like zero-where. I think in the future everything will be zero-where, but not everything is going to have zeros, yeah.
I noticed you didn't mention Glow, and I'm just curious, not to be religious about it, right? But how do TVM and Glow fit into the ecosystem, and how are they different in your perspective?
So TVM targets so many backends. Glow has been like an accelerator compiler. So I think especially the work that Andrew and I have been doing is largely, we've optimized something on x86, and then folks are like, hey, we want to ship this to phones, and then boom, we need to now have it in ARM. TVM fills that gap very, very well for us. So that's kind of how it's been filling out the role at Facebook, I think.
Yeah, like broadly, we'll have more to announce soonish, but yeah. Sorry, we'll have more to announce soonish, but yeah, we're sort of converging those two, which is a net benefit.
Question about when we see now more and more deep learning frameworks such as PyTorch and MXNet and even TensorFlow try to align with the concept of TVM compiler. How do you see the concept of unified model representation like ONNX still relevant or even contributing to the TVM concept of compiling on deep learning models? Thank you.
Yeah, it's an interesting question. I think the ideas are somewhat orthogonal. ONNX is more of like a serialization format. And I think it is still definitely compatible with the ideas. I don't have much experience dealing with ONNX or interacting with it. But I think when it comes to unified representation that can be shipped around, it is still a very useful tool.
Okay, let me see that. Oh, so the integration has support for training?
So there is a PR up. You can check it out. That does add this support. It is a work in progress. But because of the various ways you can actually extract IR from PyTorch now using lazy tensor as an example, you basically just get a compute graph, even if it is a training compute graph, and all of that can be run by TVM.
Great. One more question here.
I think sparsity is very interesting, but modern networks use heavily use depth-wise convolution and point-wise convolution, and those are very difficult to regularize with either L1 regularization or L2 regularization. Have you done any performance experiments to see what gain can be achieved with those networks with depth-wise convolution and point-wise convolution?
So I think a paper worth checking out if you haven't was a work done by one of our old colleagues, Murat, now at Google, called Efficient Sparse ConvNets, submitted to ICLR next year, which does demonstrate, in the case of, say, MobileNet v2, getting to 80-90% sparsity on the dense layers and achieving, a couple, a factor of 2 or 3 kind of reduction in effective flops, or effective performance on ARM and x86. So it's definitely achievable on traditionally factorized depth-wise separable models like MobileNet v1 and v2 and v3. So is that responsive or? Okay, thanks.
All right, let's thank our speakers again.
Thank you.